why it's distorted. I don't know how to fix it. That's weird.
Remember that? Space camp? Oh, space camp.
My niece went to space camp instead of my wedding. It's really nice.
I know I was with you. I remember today.
That's funny. He's like, I don't know today. You want me to have to go to space camp? What?
Space camp.
Huntsville's great.
What? That's for we were all there. Say yes. I can't remember.
Oh, I'm sorry.
Really?
It's awesome.
That's like fuck radiation side effect thing. I have super memory. I remember what I ate for dinner.
Yeah, there should be a whole bunch of them on the table. Have whatever you'd like. Y'all help yourselves, okay? Do what? Everyone has stolen? Oh, hold on. Y'all, doesn't anybody have any crackers for poor Piper here? Oh, everybody has one tired cracker. Hold on. I'll give you half of mine, Piper. How's that? I'll share half of mine. That's good.
Great job.
Oh, no.
We got to spell monastery.
I can't seem to make that run. That's fine. Okay, so what were we modeling in lab? What were we modeling?
Pangea.
Play Tectonics.
Pangea, plate tectonics. Anything else? Anybody else want to say what it was? What did we model?
Millions of cracker lives.
Cracker lives. Okay. Crackers falling apart. Yes. Okay. So you guys, we were modeling plate tectonics here. Plate tectonics, how Pangea split apart into what we currently see, and what kind of currents was causing that movement. What sort of heating currents?
Convection.
Yeah, convection is what we're looking for. So convection currents are uneven. And the idea is that as the warm magma, or in this case, your soup, rises to the top and then cools down because it's reached the surface and there's something warmer underneath of it, it sort of makes a circular pattern. Why do I have lava lamps up today?
But they're cool.
They are really cool.
Demonstration.
Yes, they're amazing.
This is exactly convection current. That's why they're here. So if you've never seen a lava lamp, anybody never seen one before? Everybody's seen one, right?
I've got to put my hand too long.
They're awesome, right? Yeah, they're very hot. Don't touch. They're very hot. But yes, that's what we're seeing is convection currents. I've had this one since I taught at the school. So since before Cole was born, it's an old lava lamp and it's doing fine. And then I got that little orange one because it matched our stuff and it's super cool. It's actually wax that's in there.
Yeah.
Really kind of neat. You can watch it sort of.
The mellow mushroom in Swanee is all lava lamps.
I love lava lamps. They're very pretty. They're fun to watch.
Right.
Whoosh. All right, so be sure that you give everybody chances to answer by not shouting out. And let's see what we can do with this lesson. Oh, I don't think most people even notice this. I don't think my family noticed, but Bunsen has gone to the giant fishbowl in the sky. Yeah, I did. Well, he spent more than a week like laying on the bottom of the tank, and then every time I would try to get him to come up, he'd swim for like 2 seconds and then he'd sink back down, and it was getting really sad. So I had to Google like how to euthanize a fish, because I just couldn't let him live like that. It was not good. It was not good. He was like, his fins were falling apart. I was like, you just won't die. But truthfully, that fish was over 3 years old, a beta. So I got another one from a breeder, because I'm never getting them from a pet store again after having one that lived for 3 years when I got it from a breeder. So I've got another one from a breeder, and he should be here tomorrow. And he is what they call like candy striped galaxy. Like his colors should be off the wall. Yes.
What elephant was it?
It's up in the pub. It was the Thomas Kincaid one with all the jewels, kind of ivory colored with lots of jewels. So yeah, it's lots of fun.
What happened to my bid?
Oh yeah, just sat there in the bottom.
Yeah, and then one night.
Yeah, I waited and waited and waited for him to die, and then I thought, this isn't nice. You know, first I thought it was because it got so cold out, and I thought, well, maybe he's just cold because the atmosphere is cold, and that slowed him down because he's an ectotherm, right? That was not the case. All right, so anyway, new fish should be here next week. I'm naming him Fraunhofer. And if you want to know why I'm naming him Fraunhofer, look up Fraunhofer and see what Fraunhofer did. All of my fish have been scientists. So Fraunhofer has to do with the fact that he's very colorful. So anyway, so plate tectonics, here we go. So our background knowledge. You've been asked for background knowledge anywhere else today? Oh yeah, in your lab. So Isaac Newton was one of the first scientists to develop theories about the structure of Earth. Based on his studies about gravity, Newton calculated the average density of the Earth and found it to be more than twice the density of the rocks on the surface. Newton realized that the inside of the Earth had to be much denser than the surface. I guess this, when you're Isaac Newton and all you do is think all day, things like this occur to you. And I suppose it had never really occurred to anybody else to think about it in that way. Pretty cool. So we have layers. And what are our layers of Earth? Anybody want to go? Okay, Piper, you go first. What's this one going to be? All right, that's going to be our crust. So this is your solid rock on the surface, and its thickness is going to be between 3 and 30 miles. So it depends where you are. All righty, Milo, how about this one? All right, we got our mantle. This is your semi-liquid layer of magma or molten rock that moves due to convection currents. Today, your mantle was what? The tomato soup, right? Okay, how about this one, Yusuf? Yellow. Here we go. Yellow is going to be outer core. So yeah, we're at the core. Outer core. This is the liquid part of the core, which has a similar composition to the inner core. And then lastly, all right, Liam. Inner core. All right. And this is the solid part at the center of the Earth. And it's made of iron and nickel and has temperatures rising close to 5,500 degrees Celsius. That's really hot. By the way, my skirt is layers of rock today, if you didn't notice. It's crust. You know, I always have something going on. Wait till I wear my earthquake one. That's cool too. So anyway, the continental puzzle. So did you notice anything about the shape of the continents? Well, you know, Al Gore's classmate did.
Did they ever fit together?
Did they ever? That's ridiculous. So yeah, right. So who's this dude popping up down here? Anybody know who he is? Oh, do you know who he is? Okay, very close. Okay, so when you see a German scientist's name, so this is the name we're going for here. Now, it looks like Wegener, right? But when you are doing it in German, W's become V's. So it's Wegener, Alfred Wegener. Yep. A German scientist noticed that the coastlines of South America and Africa look like they could fit together like a puzzle. Okay, when did this guy live? Anybody know? Do you know?
I was gonna say early 20th.
Yeah, did he live before or after Al Gore's teacher, do you think? I'm thinking before. Alexa, when did Alfred Wegener live?
According to an Alexa Answers contributor, Richard Wagner.
No,
the German
he's a great composer. That's not who I was looking for. Alexa, cancel. Anyway, yeah, Wagner is astounding. You know who Wagner is, right? Wagner, probably most famous, well, he was an operatic composer, probably most famous for Flight of the Valkyries, which you've probably seen as a Bugs Bunny. Killed a wabbit, killed a wabbit. That's what I'm talking about there. Okay, yeah. So just for sure, Alfred Wegener lived, okay, he died in 1930. So I know that Biden is really old, but I'm assuming he was alive when his teacher was alive at the very least. Okay, so in what year did he propose his hypothesis of continental drift? Now we know he died in 1930 and he was born in, what? I just closed it. He was born in 1880, do you know? We'd have been really old. 1915. So 15 years before he died. All right. He proposed his hypothesis of continental drift. All right. So anybody know what year Biden was born? I think he was born around the same time as my dad. So 1942. So I'm assuming his teacher was probably 30 years older than him. So yeah, she should have known. All right. So continental drift. This is that the continents had been joined to form a single supercontinent, and it was what, Milo? Pangea. There we go. Before Pangea, after. I love that. Before, after. It's like a home project, home improvement project. So, all right, let's go put some things in here. So he hypothesized that over the last how many years the continents broke apart, drifted slowly to their positions. Does anybody know how many years? Want to guess? Alex, you want to guess?
Sometime around 65 million years because of the fossil links from dinosaurs in South America and Africa.
Bigger than that, even 200 million. Big, yep, a lot. Okay, 200 million years, the continents broke apart and slowly drifted to the positions that we see them in today. All right, so we've had various configurations. So this is what we're thinking was about 225 million years ago. Then we get to like 150, 100, and then today. So it didn't go straight from Pangea to what we see today. It went through different phases. This one where you have Laurasia and Gondwana, and then we kind of had some Australia stuck to Antarctica and North America stuck to Europe up here. So we have had times when they've been in different configurations. So scientists need evidence to back their claims. So what do you call traces of ancient animals that were found in South America and Africa? What do you...
Evidence?
Wait a minute, hang on. Hands up, Drew. Yeah, that's a hard one. Yeah, fossils. Piper second guessed herself. She's like, wait, no, is it really what I think it is? So, yep, I'm going to drop coins all day. This is what I do. I throw money. All right, so fossils are traces of these ancient animals. And in this case, when we're trying to support this theory, we find that there's some in South America and in Africa that are the same. In this case, this guy here was the same, and this guy here was the same. And then look, something came all the way through here, this guy here, and this dude here, here.
Like a flower.
Yeah, it's some kind of a plant. It says it's a fossil fern, but I don't know. Glossopteris, I don't know about. I did know a guy who showed up to teach one semester in my college as a visiting professor, and he was a paleobotanist. Have I told you about this dude? He was a paleobotanist, and he studied ferns. That's what he did. He studied ancient ferns. So what is a reptile that could not have lived in salt water? Which one did he talk about here in particular? All right, Yusuf, you know. There you go. It's a Mesosaurus. That's this dude right here. Okay. So he could not have lived in salt water. So if you find Mesosaurus fossils in South America down here at the bottom, and in Africa down here at the bottom, when you look at the globe today, that's a long way. So you're talking about going from here to here. That's a long, long way. And if he can't get in salt water, can't live in salt water, there is no way that sucker swam. Like, that's not happening. So this gives a clue that South America and Africa must have been joined at one time, because there's no way for him to walk around, right? And we haven't found fossils of him anywhere else. So again, you have to think like a jigsaw puzzle. So today there are matching types within mountain belts on different continents. So matching types of what? What are we talking about here? Do we know, Piper?
Minerals?
You're real close there. So yeah, rock types, minerals would be the same idea. Yep. So when you have rock types that are the same along belts on different continents. So if you look here, like where the little red dots are and where the little black dots are, it's similar types of rock. Well, isn't that interesting that you got it here and here? It gives, and plus look at the shape, right? So when you start putting those things together, it gives you ideas. Now the Appalachian Mountains, where are the Appalachian Mountains in the US? Where are they?
Vaguely eastern seaboard.
Far away, nearby?
I'm hereby.
North Georgia. Very good. Okay. They're right here, right? We're at the foothills of the Appalachians right here. If you go just a little further north, you're in them, right? They run all the way up to like Maine. All right. So the Appalachian Mountains in the US are in what and what? In the US, and mountains in where and where are similar rock types and ages. So look, Not in this picture, so it was in your reading. Yusuf, what have you got? Okay, so Britain and Scandinavia is what we're looking at for that. So anyway, if you think about the Appalachian Mountains and where they are, okay, so where are they? They're right here, where we are, right? And then Britain and Scandinavia, right there, again, on the opposite side of the Atlantic. So how are we getting the same rock types and the same fossils? Well, stuff was stuck together. So this is another type of evidence. So Wegener also found evidence of similar climates on different continents. Do you know what you want here? You know, do you know, Yusuf, do you know? You were gonna guess? Oh,
Like you can find the same type of climate in like
Mhm.
the ice.
yeah, so ancient climates, right? So ancient climates. So Wegener also found evidence of these similar ancient climates on different planets. And you can see here, this used to be, they're calling it a coal swamp. Well, why do you suppose they're calling it a coal swamp?
There's coal in it.
There's coal in the swamp, or what do you, coal in the swamp? What do we think? What do you think, Piper?
Because there's a lot of coal in it, like.
Okay, we're getting there. We're getting there. So
What?
where's coal come from? Yeah, you're getting there. Where's coal come from?
Trees
Hmm?
and plants.
Yeah, coal comes from dead things. Coal is dinosaurs, but predominantly it's swamp dinosaur. It's swamp vegetation is where most of it came from. All right, look right here. This is where you're going to find large deposits of coal. Can you find it other places? Yes, but where there was a swamp at one time, you're going to find lots of coal. Oh, gee, is this, I don't know, West Virginia maybe, like right here? Oh, what do you know? Oh, yeah? There's all kinds of stuff through here. And then you can see where there used to be, like they're calling this salt deposits. Okay, so through here where you're going to find salt deposits, salt mines. So that gives you some interesting idea to what used to be there. And then reef. Reef used to be here and here. So you can see where a reef used to be because you're going to find coral, right? You'll find coral deposits left behind. So over time, do you think the swamp and the reef were there at the same time? I mean, that doesn't make a lot of sense, right? So over time, this area has been multiple things, and that's what it's telling you. So deposits of glacial sediment on continents that are now in tropical climates. Also rocks scratched by glaciers. So what's the word here for this kind of evidence? Do we know? Know what evidence we're looking for, Alex?
Geological, glacial, civil.
Yeah, all that kind of stuff. Okay, so glacial till. All right, you remember when I was in Nova Scotia and I picked up all the rocks off the beach with the glacial till? They're all over there in that little bowl now that I've tumbled them all and they're nice and smooth. But that beach was solid glacial till. There were rocks of every type and kind scattered all over that beach. And that's glacial till, which, so now you know there was a glacial. And then what do you call rocks that have been scratched by glaciers? What do you call that marking? Who remembers? Ooh, it's just on your midterm. Drew, do you know? Well, yeah, abrasion, that's it. He's like, blah, 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 blah. Glacial abrasion, that's it. So if you've got scratching, it's abrasion. So evidence that North America had tropical swamps, and we know that North America does not have any tropical swamps now, thank goodness, because it looks like we would be right in the middle of one, and that's pretty miserable. So Wegener's hypothesis of continental drift was a new radical idea, and scientists thought he was just wrong. And his hypothesis was rejected. Oh, this is so sad. Poor Wegener. So why did they reject his hypothesis? Do you know? Hang on. Go ahead, Chloe.
I didn't know. Because he couldn't explain how or why the continents.
My girl has it. Yes, he could show the evidence, which is basically what he's giving. So if he's showing the evidence, he's showing a fact, right? This is what happened. But the theory, right, the why, he was lacking the why. He couldn't tell people why things did or how it happened. Just, well, clearly they used to be together. And people are like, yeah, okay, how to move. So you've got it exactly right. He didn't know what caused him to move. So eventually we get technology, and that's going to lead to newer discoveries and acceptance of continental drift because Wegener was right, despite what Al Gore's teacher said. So what early evidence suggests Earth's continents might be moving? Give me some examples, Piper.
Fossils being in.
Fossil evidence. That's a big one there. Fossil evidence. Bailey. Sometimes. Yeah, sometimes. Yeah. So which ones have we done? So fossil. Yep. Mountain ranges. Yeah. Okay. What else? There you go. Ancient climates. That's one. So let's look at the ones we've gone over. Fossil, ancient climates, Alex, glaciers, Caitlin,
Soil types.
soil types and stuff. Yeah, soil types and yeah. Coal swamps. Yep. Okay. How about rock types? Don't forget your rock types in there. Okay. So yes, we've seen that there is evidence that they've moved. So the three types of evidence outlined in his theory were what, really? We just said them. They were fossil. What else? Rock and ancient climate. Fossil, rock, ancient climate. Those are your big ones. So why was Wegener's hypothesis rejected by most scientists? Chloe said it because why? He couldn't explain why. And they were like, oh, go away. You can't explain it. So what are sound waves that are emitted to calculate distance to an object? Okay, Chloe again. Sonar. Very good. All right.
Or radar if you're in the air.
Or radar if you're in the air. So, okay. We're adding all kinds of fun things now. All right. So yes. So radar if you're in air, sonar. So sonar bounces sound waves, right? And it calculates a distance to an object. Do we use sonar anywhere else besides on boats and things? Where's an example of where sonar is used in, how about, what were you going to say? Dolphins use sonar. Yeah, they use a type of echolocation. Yeah, like bats do the same thing. Liam, what were you going to say? Yep. Okay. So who can tell me what's an example of how we use something very similar in medical technology? Kind of. Oh, hang on. James was thinking. He's thinking. That's it. Ultrasound. There, sister helps you out. Ultrasound. You get an ultrasound of anything inside your body. It doesn't have to be just babies. We do them for babies, but we also do it for gallbladders and all sorts of things. There you go. So the ocean floor is not flat. So we have a part of the ocean that forms the deepest parts, and they occur at the edges near the continents. What do we call these? All right, Yusuf.
Deep sea trenches.
Okay, deep sea trenches. We got our deep sea trenches, and they're going to be, where are they in the picture? Do we see one here? Is there one here? Yeah, right here. There's one here. There's one here. All right, so what do you call the long chains of mountains in the center of the ocean? Liam. Okay, all right. So mid-ocean ridges or oceanic ridges or however you want to do it. And then what is this Central Valley location occurring in the middle of the mid-ocean ridge? And it looks like a big canyon. All right, Piper, do you know? Change your mind? Drew, was that a hand? No? What now? Sort of. All right. You know, Yusuf?
Mid-ocean ridge.
Okay, so what we're looking for is a rift valley, but yeah, you guys got the idea, right? All right, a rift valley. So now we're getting into one of the other things I think is one of the coolest take home, keep in your brain forever. Like definitely want to keep, I forgot to put a RICO in this lesson, but there should be one for convection currents. But one of the ways that we've proved that the whole planet has changed is by studying the floor of the ocean. And we've learned some really neat stuff about polarity when it comes to the ocean floor, and it's way cool. So what is seafloor spreading? So what happens here is you've got magma right here that's getting pushed out of this mid-ocean ridge, and it's forming this rift valley, right? It's getting pushed out of the mid-ocean ridge, and this is this long mountain chain, and it's getting formed because as that magma is coming up, pushing out, it's building right onto these mountains beside it. The magma spreads along each side, it cools and hardens into rock, which becomes oceanic crust, and more lava forms at the ridge, and then it pushes everything outward. So ocean crust is young in the middle and old at the outside. Now, as this ocean crust moves away from the center, in this case here, you've got a continental plate, and it's going to slide under, okay? And that's what we call subduction. We'll get to that in a minute. But when a plate comes in contact with another plate, there's only but so many behaviors, only but so many things that can occur. This is where I think it's super cool. This is a, woo, keep it in your head, neat fact. So magma that cools and forms on the ocean floor is rich in iron, all right? Now, iron's magnetic. Now it's coming up and it's coming up out of the ocean floor and it's doing this, but it has iron particles, flecks in it, basically, right? And the rocks cool unevenly, like we've seen, right? So you've got little, almost like chunks of iron. And as it's still liquid, that iron aligns with the magnetic poles of the planet, right? And so you've got your positives one way and your negatives one way, and they're all going the same way, all right? So when the magma cools, the grains in the rocks line up with Earth's magnetic field. Now, the rocks acquire the polarity of Earth's magnetic field at that time. What do we call that? So we call that paleomagnetism. Now, here's the important thing. At that time. What does that mean? The polarity of Earth at that time. Alex.
The polarity of the Earth's magnetic field switches, don't remember how often, it was like 500,000 years, 50,000 years.
Yeah, it's a long time, but it does switch is the point. So we have a north and a south, and that's the way we've always known it. All of humanity has always known this. Our compasses have always pointed this way. This is the way we've always known things, but it hasn't always been that way. And we can prove that because when you look at the bottom of the ocean with the right equipment that can detect the magnetism, come on, hello, you can actually see the striping switch direction. All right, are we not gonna play? Do I have to hit escape? Stupid, hold on. Oh, why it's doing that to me? Oh, be that way. Fine, I'll just go over here. Do it over here. Because it should, I don't know why it's doing that. It's also stretched my whole thing out weirdly up there. Goodness knows what's gonna pop up here. Oh yeah, pull up all kinds of fun things. Look at that, it won't even type. It's so fast, but when it's plugged into all this stuff, it gets all weird. What? No, I want this one. Where is it? This one. Here we are. So this is cool. Let's hope we have sound, because I don't know if we do. We do.
This is an alien world. There is no light except that made by bizarre creatures that live here. There is no sound but the bubbling of hot sulfurous vents. It's a world that very few humans have ever
Hello.
And yet, this is a part of our world. We know less about the deep oceans of planet Earth than we do about outer space. The oceans are deep, dark, and full of mystery. Most of what we do know about them was only revealed in the last 60 years, when technology was finally able to see through the immense expanses of water. We now know that the ocean sits on top of oceanic crust, just as the familiar continents are fixed to continental crust. In the 1950s, a group of scientists became interested in the oceanic crust, and in particular, its magnetic properties. What they discovered changed how we understood not just the oceans, but the entire history of the Earth. I'm Ruth, and today I'm going to talk to you about magnetism at the bottom of the ocean.
Hi, Ruth.
Consider a sailor's compass. The idea behind the compass is that it will always point northward, allowing the user to navigate across a featureless ocean. It is influenced by the magnetic field generated in the Earth's core. Sailors have used compasses for many centuries. However, a compass can be influenced by forces other than the Earth's magnetic field. In the late 18th century, sailors from Iceland noticed local disturbances in the magnetic field that caused navigational errors. The disturbances were put down to magnetized rocks on the seabed around Iceland. In World War II, a new instrument was developed that could be placed on an airplane and used to detect submarines in the Atlantic Ocean. This device was a special kind of magnetometer, an instrument for measuring magnetic anomalies. After the war, it was modified and used to identify those disturbances the sailors had encountered. Planes flew back and forth across the Atlantic with magnetometers on board, creating a magnetic map of the seabed. Scientists knew that the rocks making up the oceanic crust were mostly volcanic, and they contained magnetite and other magnetic minerals. However, the scientists didn't expect them to form any particular pattern. Magnetic anomalies would be randomly distributed across the seabed, or so they thought. When the first magnetic surveys were finished, scientists were absolutely blown away. They did not expect what they actually saw: stripes of magnetic anomalies that switched between positive and negative. They saw a positive stripe next to a negative one, next to another positive one, and so on. What caused this pattern of magnetic stripes? It turns out that the Earth's magnetic field is not entirely static. It moves over time, which causes the north and south poles to drift slowly. Every few million years, it even flips around, so north and south are completely switched. When the rocks in the oceanic crust are formed, they preserve the direction of the magnetic field at that time. If it matches the direction of today's magnetic field, it can be measured as a positive anomaly. If the direction of the magnetic field is opposite, it can be measured as a negative anomaly. However, even this revelation doesn't explain the stripes on the seabed. To form stripes of alternating positive and negative anomalies, different parts of the seabed would have had to form at different times. In fact, the whole seabed would have had to have moved over time. In the Atlantic Ocean, the magnetic stripes are symmetrical on either side of the mid-Atlantic ridge. Rocks on either side of the ridge have preserved the imprint of the current magnetic field and are geologically the youngest rocks in the Atlantic. As we look further away from the ridge, we observe the well-developed magnetic stripes. We can also see that the rocks get geologically older toward the eastern and western edges of the ocean. This model demonstrates how the seabed itself must have moved over time. The two strips of paper represent sections of oceanic crust that emerge from a mid-ocean ridge in the center. As molten rock is erupted at the mid-ocean ridge, it cools and solidifies, preserving the orientation of the Earth's magnetic field. Then the orientation changes. The magnetic field flips, and this change is recorded in the younger rocks. As more and more rocks are added in the center, the oceanic crust spreads further and further out. The magnetic stripes develop as the magnetic field keeps flipping back and forth. In the Atlantic Ocean, this whole process took 200 million years. It was very, very slow going. In order to produce the pattern of magnetic stripes that was discovered in the 1950s, the seafloor had to spread out. The Atlantic Ocean actually grew over 200 million years, and the continents on either side had to separate from each other. It sounds crazy, but this is the only reasonable explanation for how magnetic stripes were formed. Actually, that sounds a lot like Wegener's idea of continental drift, except it was given a new name: plate tectonics. Magnetic striping was a key piece of evidence in proving Wegener's ideas correct. Unfortunately, he didn't live long enough to experience the satisfaction of being right. Not only did the discovery give sailors the data they needed to correct their compass measurements, it also paved the way for a bold new scientific theory. Plate tectonics underpins our entire modern understanding of how the Earth works. It explains how volcanoes and earthquakes occur, how continents shift over time, and how the planet itself has developed. If you want to go back in time, studying plate tectonics is as close as it gets. The theory allows us to look back in time, reconstruct ancient continents and oceans, and visualize the prehistoric ecosystems that lived in them. Time is as deep as the ocean, and there is plenty of it still to explore. I hope you found this video helpful and you're keen to learn more. Thank you very much.
So you've got these, you've got these magnetic stripes, and they show how the polarity has been over time. And personally, that's I think that's one of the neatest things that in this whole class. Like, to me, that's just fascinating that it took till basically World War II for us to realize that proof of spreading was shown in little iron fibers or particles within. What do you need, hon? You need a place to sit, or pull a chair over here, and the floor. Okay, so the ocean floor is, what do we want here along the Rift Valley of the mid-ocean ridge? What did we just learn about the ocean floor here? What's this map show, James? It's the youngest. Yeah, that's your youngest rock. That's right there. It's exactly the same picture, or almost exactly the same picture that was just in the video. So the ocean floor is the oldest near what? In the what? Go ahead, Bailey. Yeah, so it's going to be actually near subduction zones, which are right near the trenches. There are trenches that cause those subduction zones. So that's right. Right near the edges of the continent. So this is where you get your oldest, obviously, right there. All right, so how do ridges and trenches support the theory of seafloor spreading? Somebody sum it up for me. Sum it up, sum it up. Who's gonna sum it up? Da, 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 da. Randomly calling somebody. Ridges, trenches. All right, Chloe, go for it, you brave soul.
Okay, so lava comes out of the ridges, cools, and then moves the stuff next to it into the trenches.
There you go. And that, well, the trench is kind of in the middle of the ridge, right? And there you go. You got it. All right. So how are ocean floor rocks and sediments evidence of ocean floor seafloor, spreading? How are rocks evidence of spreading? All right, Yusuf, what you got?
Because the climate.
On the seafloor? Think about seafloor. Jack?
Is it the magnetic,
That's a big part of it. Yeah, there you go, your magnetic stripes. So, and these are kind of the same questions, one backs up the other. So how do the magnetic stripes support seafloor spreading? Well, when you see them, it's obvious that it's taken a long time for that floor to move, and clearly it has moved because you can see the polarity switching. So last one is, what would Wegener say after seeing this evidence?
I don't know, I don't speak German.
What do you think? Told you so? What do you think?
No, I don't speak German.
Yeah. Yes, I told you so, people.
You guys
I
are
speak it.
stupid.
Oh, no. All right, so let's see what's next here. Theory of plate tectonics. So now we've taken what Wegener was calling continental drift, but he couldn't explain how it happened. And then other people come in and they say, oh, now we're going to call it plate tectonics because we sound really smart and we're going to, we know how it happened. So nanny, we're not going to use your title anymore. So the lithosphere is broken into several huge pieces, and we're going to call these plates. And then we have deep faults that separate the plates. So the theory of plate tectonics is basically this: Earth's lithospheric plates move slowly relative to each other, driven by the convection currents in the mantle. This right here, if you were looking to, I don't know, put background information on your lab, and I always save these where you can find them. All right. We got 3 types of plate boundaries. Somebody give me one. All right, Yusuf, give me one. Okay, Liam, give me another. Okay, and Alex, give me the last one.
Sliding boundaries.
What do we call this?
I don't remember the name.
All right, you're fine. So here's what we got.
It has something to do with friction.
Transform. There you go. All right, so divergent, convergent, and transform. With your hands, everybody. What does divergent look like? What does convergent look like? And what does transform look like? All right, everybody's got it. Not too tricky. So here's your divergent. Moving away. Divergent boundary is a boundary where 2 or more of Earth's plates move away from each other. So Earth's crust is what at the divergent boundaries? What's going to be special about the crust? Alex got it. It's going to be younger at a divergent boundary. Is there what type of boundary is in the mid-ocean ridge there, right along the trench? That's going to be divergent. Yeah. Okay. So notice here, this is a graphic of convection current, and this is showing what would be occurring there at a divergent boundary underneath, if you could see it. All right. So then we have convergent. So your convergent boundary is where 2 plates collide. And you got 3 types: ocean-ocean, ocean-continental, and continental-continental. So, and this is where you have a subduction zone. When they're coming together like that, one's going to slide under the other. Whichever one is denser is going to slide under the other, right? So some oceanic crust, what happens to the oceanic crust at a convergent? Yeah, it's destroyed. Exactly. It's destroyed. It goes under the continental plate, right? And it gets destroyed at that convergent boundary there. And that would be at what kind of zone? That would be at an ocean continental, right? All right. So transform, slippy slidey, right? Your transform fault boundary is where 2 plates slide past one another, but crust isn't what? What? We talked about young crust, and then what do you think it is?
Or destroyed?
Wait a minute, what? Piper. Yes, Piper was going to say what he just said. Created and destroyed. That's right. So it's not some crust is created and some is going to be, it isn't created or destroyed. Sorry, I can't speak. So you got created at your divergent, destroyed at your convergent, and really neither here. And you can, if you see real quick in that graphic, do you see how it can't really even show you the direction it's turning, because it's more like it's turning on an angle, to push them in different directions from each other. All right, so let's run through them again and make sure we got it all. So what's the theory of plate tectonics? Somebody explain for me. All right, Yusuf, you want to give it a shot? Or no, Alex?
The simple atmosphere here.
That's what I'm looking for. Yeah, we don't have a year.
Lava is as well. It would be magma turns
Correct.
to lava at that point.
We're with you.
Forms, bubbles up along the mid-oceanic ridge.
Mhm.
It expands the crust on either side, pushing everything else away.
Mhm.
Eventually, it meets somewhere Pacific Ring of Fire, I believe, like somewhere mid-Pacific.
That's
is
pretty
where it
good.
combines, and that's also what A causes the Ring of Fire. B causes the Himalayas to get taller.
Yeah.
To
Mhm.
At least I think it's that one that causes the Himalayas to get
Mhm.
taller. And it also causes continental drift and the
Right.
break apart.
Anybody have anything to add to it? So basically, you've got plates. The Earth's lithosphere, keyword, is broken up into plates, and they float around on the mantle, which is kind of semi-liquid, right? And as convection currents cause the molten rock, the magma within the mantle, to sink and fall, it creates basically a form of friction underneath and either pulls plates apart, pushes plates together, or causes plates to slide back and forth along each other. So our 3 plate boundaries are, we can say them together: convergent,
Divergent, transform.
What happens to crust at divergent? You get what kind of crust?
New.
New crust. And at convergent, what happens to crust?
Destroy.
It gets
melts
destroyed.
down.
And then it transforms? Neither. Okay, good. The ocean floor has been compared to a conveyor belt. How would you defend that comparison?
It ends up moving and eventually would cycle around theoretically.
It really is. Yeah. If you think about it, like at the grocery store, if the grocery store, when you put your food on the conveyor belt and it goes to the end and it stops, what kind of boundary does that kind of look a little bit like?
Like seafloor, where's seafloor?
I would say it's convergent. Yeah, I would say it's ocean continental, because you've got the belt comes this way, whoop, and it sinks down, right? It goes right. It's almost like a subduction zone, except that this one's not moving as much. But yeah, it gets sucked right under. So the conveyor belt that goes round and round like that, that's kind of like the way that the ocean floor moves. And now you'll look at conveyor belts at the airport that have your luggage on them and think, oh, no, you won't, unless you're me. All right, so
No, I'll just wonder if I can get on them and ride them.
it does look fun.
Yeah, okay.
It does look
They
fun.
did it.
It does look entertaining.
Boys, not me.
So what are the mechanisms here of plate motion? All right, so we talked about convection currents. So convection current, this is the continuous flow that occurs in a fluid because of differences in density. Warm material is less dense, so it rises. Cooler material is denser, so it sinks. Okay, now when we talk about things rising, it's sort of, okay, when you're trying to describe things like air or any kind of fluid, air, water of different densities, rising and sinking, it isn't really that the less dense air or water or whatever fluid rises. It's really that the more dense falls because gravity's pulling on it and it pushes the other stuff out of the way. It displaces the less dense stuff. So, you know, what's going on here? It's not really like this is floating up with some power of its own and defying gravity, because gravity is what's working on everything, right? Gravity is affecting that whole thing. So the only way that is working against gravity is if the fluid around it is coming down and pushing it up. So you kind of got to keep that in mind, because we kind of colloquially say things like hot air rises, and it does, but it doesn't do that of its own power. None of it's doing it of its own power. But you have to think, if it's going to do it and defy gravity, like cold air sinking, okay, cold air sinks, it does. Why? Because gravity pulls it down because it's more dense. But that doesn't mean that warm air floats or rises because it's less dense. So when you think about it that way, you really have to think about it as the more dense fluid displacing the less dense. Okay, so convection currents in the mantle provide the basic driving forces for plates in motion. All right, oceanic crust is coldest and most dense far away from the mid-ocean ridge. And what do we call this? This is known as what? Do we know? So this is this term here. All right, so this is what we're going to call slab pull. So you have to think of this as a slab. All right, so in this case, it's being pushed, right? It is actually being pushed here, but it's also being pulled down. And it's being pulled down because this end of it, again, this is what we were just saying, this end is more dense, it's colder, the rocks have solidified, and it's more dense. And so it's actually being pulled towards the center of the planet. So while this is being pushed, the other end is also being pulled, and we call that slab pull. So near the mid-ocean ridges, the asthenosphere is elevated. Oceanic crust slides down this elevation. And what do we call this? Do we know? Do you know?
Ridge push.
Okay, very good. This is actually ridge push. This is right. So you have a slab pull and a ridge push. So this makes sense. You can really see the slab pull and then a ridge push. So you've got this slab and it's moving like, almost like think of a conveyor belt. Same idea. So right here, if it's going this way, it's being pushed at the ridge, but it's being pulled at the other end. And we call that slab pull. Makes sense, right? It's not just being pushed, there's pull happening. And that's because, like we just said, it's more dense. So it's getting pulled down towards the center of the earth. All right, so watch these images. These are great. So these are convection currents. In the middle one, you can actually see it. There's an RF of you can see it go up and down. Woo! Like if you could see what was going on in your pans today, that was it. See it cycling? Now, some of you may have noticed that your crackers didn't pull right along that middle ridge like you expected, or maybe some of you hypothesized that some of them would get pushed and some of them would get pulled. But what most of you probably found out is that every one of those hot plates had different hot spots. Did you notice that? There were spots in your pan that just got way hotter than others. And that's because they're uneven. The hot plates are uneven. Like if you had some like $5,000 hot plate, it probably wouldn't be, but that's just a normal hot plate. So it's somewhat uneven. So you see spots that get warm. This is probably also true when you put a pan on your stove. You probably also find that there's warm spots, especially if you have electric burners, not gas burners. Same is true of a grill.
Yeah, one time I put my bread, like I was making sandwich, and I put my bread, I went for 2 minutes. One part was just the plain bread, the other part was like crunched up.
Yeah. I think we've all experienced that at one point or other. We're like, oh, this is jacked. How do I fix this? Like, there's no way to get this right now. So yeah, so you're gonna have hot spots. And truthfully, Earth has hot spots too, right? Earth has hot spots kind of everywhere. So
like the
that's-
super volcano under
There you go.
Yellowstone.
Yeah, wherever
Life
you-
out the-
right.
Almost all life on the continent.
And so all along your mid-Atlantic ridge there, you've got hot spots in the trench, right? That's where it's coming from. So in your tiny model that you made inside your like 8-inch pan or whatever that was, you probably had some hot spots. Did anybody have more than one cracker divide? Or did everybody just have one? You had more than one?
We got two.
You got two that went? How about you? Two? So for those of you that had more than one cracker that divided, did the halves go the same direction or different directions? Different. So you had different hot spots in different places, or were they placed along the same hot spot and the orientation of the cracker caused
There
it?
were two that were, we had two of them that were on hot spots and one that wasn't. And the two that were on hot spots did move apart.
Okay. Yep. Sometimes when they're right on top, it doesn't get enough of the current on one half or the other half to move it. Yeah.
Ours fused together for the first half,
Mhm.
but then when we cut them apart, we just picked one.
Right. I've been doing this lab for years and years and years, and this is the first time I've ever done it on hot plates. I've always just done it like myself as a demo, but I wanted y'all to do it this time, so I had to.
I like this lab.
Thanks. It's a fun one. So I had to pilot it with the hot plates to determine like what temperature y'all should go at. And when the first time I did it, I dropped the crackers too early and they fused back together, like Drew said. And I was like, oh, this isn't good. I probably went through 30 crackers the other night and had this nasty paper towel full of gross, soggy crackers because I was trying to find where to drop them. Because if you do it on the oven, it heats up quickly enough that you can put the crackers on while it's cold and just watch it go. But here you had to wait for it to get hot first. So you've got convection currents. And that's what's within the earth. That's what drives your plate motion. Hot material within the mantle moves upward. At the same time, cooler, denser slabs of the oceanic lithosphere sink back down into the mantle. You got little images here, your convection cells. You got good graphics here. You get the idea.
It's really satisfying.
It's really cool, isn't it? It's quite pretty. Like,
It's
whee.
not even like the end part. is not-
Yeah, it's not quite, is it? It's not symmetrical. Yeah.
The part gets kind of out of control.
Yeah, not totally symmetrical, but neither's nature, right? All right, so here's what we're gonna do. We're gonna take a few minutes to kind of look over these because I know usually we just sort of skip them and move on. So we're gonna take a couple of minutes to look over these. I'm actually going to, hold on. I'm actually gonna disconnect, boom. Oh, now I can see and you can't. So I'm gonna read into you, get some answers from you guys, and then I'm gonna give you about, I'm only gonna do this for about 5 minutes. Hang on. And then I'm gonna give you guys about 20 minutes or so, 15 minutes, whatever, to work on your labs as a group. Make sure you've got together. Now, I will suggest this. Since you have to type, there's not a ton of point in writing out everything. What I recommend to you smart people is that if you have a smart device or one of you does, you pick it up and you very quietly in your notes section. And then when you get back home, you cut, you paste, and then you edit and move on. This is how to hack it, right? Hack it. You had a question.
I didn't get this. I didn't get one of the pages.
Okay. That's all right. We're going to do them. So let's see what we've got. I'm just going to pick some random questions off of here and see who's paying attention. Let's see. All right. To support the hypothesis of continental drift, Alfred Wegener did not use which of the following? Ancient climatic evidence, magnetic field data, data on ancient reptiles and ferns, and evidence of rock formations. True. Correct. He did not do that. That came later. Poor dude, if he could have done that, maybe he wouldn't have been so rejected. Coal beds in Antarctica indicated to Wegener that this continent was always cold, inhabited by penguins, once located closer to the equator, or once beneath the ocean. Bailey. Bingo.
Technically, it is also inhabited by penguins, but
It is, but I don't think that's what the coal told him, you know. True or false? Maps made from sonar and magnetometer data led to the discovery of ocean ridges and deep sea trenches. Use it.
True.
True. True or false? The oldest ocean floor rocks are about 3.8 billion years old. Bad, Drew. That is false. Do we know the right answer? Chloe?
180.
Good girl. 180 million. She doesn't even have it in front of her. All right. And true or false? The theory of seafloor spreading explains that the Earth's continents move because they ride atop ocean crust as it moves away from ocean ridges. True or false? Parker, what do you think?
True.
Yes, true. All right.
they don't go right atop oceanic crust, though,
They ride atop,
continental crust.
well, hold on. Where did it go? Where did it go? Sorry, just lost it. Because they ride atop, okay, explains that Earth's continents move because they ride atop oceanic crust as it moves away from ocean ridges. The continents are a continental crust, but the idea is that they're not floating on the crust, but they're on it as it moves under it, is the idea. Does that make sense? Kind of, sort of, kind of. I'm not going to put that question on a test, so you don't have to worry about it. Next, let's see. Okay. All right, what is a device that can detect small changes in magnetic fields? What do you call that? Jack, is your hand up or no? Maybe.
I know what it is.
Well, let's do the old science break it down thing. Something that reads ends in the word meter. And what are we searching for? Magnetic information. Wait a minute. So it would be a, yeah, that's one of those ones where you change the accent. So it's a magnetometer. Yeah, magnetometer, we don't usually go, but that's, you know, it would be, it's kind of, a lot of those words that end in ometer, we changed have you noticed that? We changed like how we pronounce or the accent. Like, what's the thing that determines your speed in the car?
Speedometer.
It's not a speedometer, right? I mean, why is it not a speedometer?
Way better.
Shouldn't it be a speedometer? Right?
I'm gonna be thinking about that.
Here's a good one. What's the thing that they pump up when they're determining your blood pressure? What's that device called? Sphygmometer. There you go. All right, now, this type of line connects points on a map that have the same age. Oh, do you know, Yusuf?
Isochron.
Isochron, good job. All right, let's do 2 or 3 more. How about, where are most divergent boundaries found? Seafloors, continents, coastlines, or subduction zones? Liam? Bingo. All right, and let's do 2 more on this page. All right, we did that. Okay, somebody explain to me slab pull ridge push. We went over it. Somebody explain it back to me. Slab pull ridge push. All right, Alex, do you want to give it a shot?
So slab pull is, well, we've got these slabs of rock and.
Continental slabs, yep,
At the very end where it's going under into the mantle, that's pulling on it. And then where the new stuff is being formed, that's pushing it apart.
Right.
Yeah, for the pull on it, it'll push it.
Right.
Together.
Pushed apart from the center and then pulled down on the edge, on
Yeah,
the bot,
pull
other
it
end.
down into
Yep.
the abyss.
Okay, so it's currently 12:58, which gives you 30 minutes to work on labs. Okay, I want to give you time because it takes a long time for those hot plates to heat up and everything. So you guys have 30 minutes. Don't get too loud. Work as a group. Be sure you have your hypothesis agreed upon or whatever, or not agreed upon, however you're doing it. And your background information and purpose. It's a great opportunity to like talk to your phone or type on your phone or divide up the work so you don't have to do as much online. All right, so you're good to go. This will be available to you as always. I'm gonna let this recording go. So Sky or anybody who's watching from home, we catch you later.